All right, let's get started, everyone. It is Monday, April 22nd. Hope everybody had a nice weekend and is ready to get started with some compilers again. So what are we talking about today? Well, we're going to continue talking about parsing, or that syntactic analysis that we've been talking about. A little bit last time we talked about ambiguity. We talked about how that can produce two different parse trees. And while, back when we were dealing with regular expressions, it was like that didn't matter, because the point of those languages were basically to say whether it accepts or rejects. But here, now that we are actually starting to encode meaning into structure, ambiguity can be a bad thing. And so we talked about how we could encode operator precedence into the production rules. And today we're going to talk about how we can do that with associativity. And then what we're going to do is we're going to start talking about top-down parsing. This is essentially what you're going to be implementing in your homework for homework number 3. But we're going to have to see that our grammar is going to need a little bit of tweaking to get there. So that's sort of what's on the roadmap for today. So in terms of announcements, so homework 2 is out. It is due Friday by midnight. There is a chance that we might look into making it due on Monday, just to make sure that you have everything that you need. This is a new, we reformulated this assignment from last year. Last year, this was a paper and pencil assignment. And so, last year you just wrote down the grammar on paper, and we had a look at it. We're not trying to make the assignment harder this year or anything, but back when you were doing it on paper and pencil, people would ask, and there was a question on Piazza that I'll try to get to. People were saying, how do I test my grammar? Well, how do you test it on paper and pencil? If it was in paper and pencil, you'd have to draw it out, and that's possible. But really, the reason why we're using Ply, which is a Python version of Lex and Yak, is so that you can actually test out your grammar. You can say, here's my grammar, give it in Ply, and then you can pass it strings, and it will tell you whether your grammar accepts it or rejects it. So, and plus I think it's fun to get a little bit of experience using some of these tools so that you can see how you can use a parser generator. But we want to make sure that you have all the material you need. So let's shoot for Friday, and I'll let you know next time whether it's going to be due on Friday or Monday, depending on how much we make through these lectures. For help, make sure to ask on Piazza. As always, no guaranteed help over the weekend or off business hours. And I hope everybody got their homework 1 in. We're going to start grading that as soon as possible and hopefully get you some feedback soon. Does anybody have any questions about what we have coming up? Yep.
Not about what's coming up, but it says missing on the canvas when I submit and turn it in. I don't know if that's supposed to happen.
Which one's missing?
Homework 1.
Homework 1? Well, you submit on Gradescope, right?
Turn it in, yeah. Right?
Yeah, so on Gradescope, we're going to look at the most recent submission up until the deadline. Yep.
Okay, yeah, it says missing.
That submission is unrelated.
Is that one unrelated? Okay.
The submission on Gradescope doesn't propagate to Canvas.
Oh, yeah, we don't have Gradescope hooked up to Campus yet.
Oh, you don't?
Yeah, so eventually we will work on it, but there's only so many hours in the day. Yep.
On the homework 1 assignment on Canvas, there was a text box, and you might have needed to fill that out.
Post on Piazza, like Riddick and Sakshi are doing Gradescope. They said Gradescope makes life easier for everybody, and so I'm not going to have very many answers about Gradescope. Make a post on Piazza, and if it needs to be private, make it private, and we'll get everything sorted out. The idea is that there's going to be a little bit of friction with it, but I think what you have to do is balance the benefits that you're getting this quarter, which is you're getting a lot of auto grading stuff versus what you'd get without it, which, as you know, is not much auto grading stuff, and then a lot of headaches when there's little mismatches and stuff like that. But so if you have issues with Gradescope, please make a private post on Piazza, and we'll get it. Or even public if it's not anything sensitive, and we'll get it sorted out. But and I want to encourage you to do that, because we are trying to iron this stuff out. It's the first time I'm using Gradescope. Okay. Any other questions or comments? Yep.
Can you say what the little optimization was for homework 1?
Oh yeah. So the one that I was thinking about that it sounds like some of you have already figured out on your own was, if you do ignore, remember you have kind of ignore as like a white space or a new line or a tab. What you can do is if you do white space plus. So what that does is that matches one or more instances of white space. And since white space appears quite a bit throughout the input files, and also white space does just occur quite a bit in input programs, matching all of that white space all at once rather than one character at a time will really help you out. So how many of you guys got that one? When you did ignore, was it white space plus? All right, a few people. If you want to go try it, it's changing one character, and you'd see a pretty big performance improvement. Yep.
The other optimization Simon and I found was, after we both completed it, was that you could compile the regex, and then you could provide an offset so long as you use the class instance function rather than the class static function.
Yeah, so that's the one that was you posted about on Piazza, right? Yeah, and that's a really cool optimization too. That's one that I hadn't even thought about. But that helps you out because strings are immutable. So when we slice strings inside of our lexer, it creates a new string object every time. What this optimization does is it keeps the string object around, and you just index into it differently, so you're not copying massive strings. And you got some pretty good performance improvements from that.
Yeah, it was about 2x.
2x?
Yeah, dependent.
Yeah. So it's kind of fun to think about how to optimize these things. And I'd encourage you to continue thinking about optimizations. All right. Any other questions or comments? We do have midterm coming up in 2 weeks now. So that's something to start thinking about. I can make a quick study guide, but I think you might, I don't know if it's going to be that useful because I'm just basically going to go through the slides and list the themes of the slides. Anything that we've talked about during class is liable to be on the midterm. So if it's in the reading but we didn't cover it in the class, that's off limits. We're not going to do that. So just what we went over in class and what's in the homework. Those things are what can be on it. So, like I said, I can make a study guide, but it is just going to be kind of a high-level overview of the slides. Okay. And then the other thing I want to mention is, we had this parallel programming educational user game study. We're still recruiting people to do the user study. What the HCI folks have said that they'll move the equipment to the main campus. So if anybody, wanted to participate but didn't want to go all the way over to Santa Clara, this time we're going to move the stuff here. And so, $30 and go play a game about parallel programming might be fun for some of you. But I just wanted to mention that real quick, that's still on the table. Yep. So it's going to be both places. If you message them and want to go to the Silicon Valley campus, that's where their headquarters is, so they'll like that. If you want to hang out here in Santa Cruz, then they're planning to bring the stuff over. So yeah, I think they're just getting a little bit desperate for participants. Okay. Cool. So with that all being said, let's start by going over the quiz. So the first question is, and I do want to mention, I don't know what was going on with Canvas and that input box. I tried to edit it, I tried to fix it. In the end, I hope you just, if you weren't able to input an answer for it, I hope you at least thought about it and reflected on it, and we can kind of remove that one from the grading. But for the questions that actually worked, what is an example of an input recognized by this grammar, where we have A as a non-terminal? Yep.
One that starts with Y and the rest are X.
The one that starts with Y and the rest are X. Can you tell us why?
Because you would go to the first, because there is no way for anything to be to the left of Y.
Yes.
So it would have to be the one all the way on the left. And there has to be something to the left of X, so you couldn't have all X's as well.
Yes. So I think that's exactly right. And the way you want to do that is you want to look at these grammars and, it's not quite, or at least for me, it's not quite always clear the types of strings that they produce. But if you were to walk through a few examples, for example, if we had our grammar here and we talked about if we wanted to try deriving XXXXY, we'd start and our sentential form is A because that's our the starting symbol. And, we could apply rule 1. Well, let's actually start. If we apply rule 2, we get a Y. That's a dead end. So we have to apply rule 1. And if we apply rule 1, we get a X. And then the other rule, again, we could do the same thing. And we could apply rule 1. In that case, we get a X. And what you can start to see is when you do a few examples of this, you can start to see that this generates strings that have trailing x's, and then maybe to terminate, you have to put a y at the beginning. So eventually you get a y at the front. So that first option that we had, that ends with a y. There's no way to get a string that ends with a y in this grammar. And again, like I said, the way to think about that is maybe not just squinting at this and scratching your head and thinking really, really hard, but actually walking through a few derivations and trying to see what strings you're able to make. So similarly with x, y, 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 we said that we can't end anything with a y, so this one's not going to work. The x, 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 y, like I said, that one does end up working because you start applying your rules and you generate a bunch of x's, and eventually when you get enough x's, and I don't know, I didn't count all these x's here, but you can terminate by applying rule number 2. That gives you a y at the beginning of the string. Similar with this one, what you could do is you realize that you are only able to get one y character, because that's the terminal case, and so you wouldn't be able to make this string. Okay, does that make sense to folks? Yep.
When it's written with this in the rules, it's written with the spaces, but when you put the string in there, there's no spaces. So I'm just a little trying to wrap my head around this. I just don't understand how can you map it if there's spaces in between the rules or whatever they're called, the terms.
Yeah. So spaces are always a bit weird. What we have up here is the spaces between your production, or in your production rules, these are either terminals or non-terminals. The spaces between them are not part of the language that it accepts. This is like its own programming language, and you have spaces between non-terminals and terminals. And then here, again, it wasn't explicitly laid out, but hopefully it was somewhat clear from the context. These capital letters were single characters. So you're allowed to have, basically the spaces in your production rules get ignored the same way spaces in your C program get ignored. If you want spaces, you need a token for spaces. And in practice, what we're going to see is that we ignore space tokens so that they just don't show up anyways. So it's a good question. And I think, that's not my plan. I'm not going to try to trick you guys with spaces on a test or anything. I'm going to make that one clear because it's pretty confusing and not for any interesting reasons. Okay. So when we go to this one and we ask which grammar is ambiguous, so is this first one ambiguous? What do people think? Elliot says yes. Is the second one ambiguous? Who says yes? Who says no? A few people saying no. What did people try to think about when trying to think about whether grammars were ambiguous or not? Is there any sort of formula or recipe you did in your head? Yeah.
Multiple terminals.
I think that's it's not required, but it is a good kind of litmus test because. And it works in this example because if there's multiple non-terminals, that means you have a choice. You can choose to expand this one or this one. When there's only one non-terminal in the production rules, you don't have a choice. You have to expand that one or you have to expand that one. And so, if you have multiple non-terminals, it's not guaranteed that your language is ambiguous. But if you only have one choice, that means your grammar is going to be non-ambiguous. So let's actually have a look. So, let's assume that E is an expression and, ID is a number. If we have 2 plus 3 plus 4, we saw this one a bit last time. So if we have E plus E or an ID, there's 2 different parse trees that we can make. And the 2 different parse trees, again, they come because there's a choice. We can either expand this E or we can expand that E. And so there was a choice, and if you make different decisions on which one you expand, you get 2 different parse trees. When there's not a choice, you have to expand the expression on this left-hand side. So, other than this would turn into an ID, the tree that would result from this grammar would look more like this one. This one would not be not be allowed because you don't have a choice to expand an expression on that side. Similarly with this one's just the mirror version. You can't expand the left-hand side, so you need to expand the right-hand side. And if you have something like this, then it's just ID plus ID, and you don't have you can't really expand anything. So really, you wouldn't even be able to match this string. Okay, is that making sense to people? Any questions or comments on this one? Yep.
I just wanted to confirm, when we talk about ambiguous, it's just about the tree, not about what it actually values to.
Right. So an ambiguous grammar, if you decouple it from arithmetic, decouple it from any meaning, what it means is that it is possible to get two valid parse trees. From the given an input, it's possible to get two valid parse trees. And that's an ambiguous grammar. Yep. Did you have a comment?
Oh, so you're saying this one's also ambiguous?
This one's not ambiguous, right? These are just example parse trees of the first one. That would have been E plus E. This one, you wouldn't even be able to match this input using this grammar because you can just match an ID plus an ID. You can't expand any of them. And?
Yeah. If we did expand it, would even if it were ambiguous, because does it make much of a difference considering addition's associative?
Yeah, well, I think that's kind of the next question coming up on the quiz. So let's see. Well, let's get there because it's coming up. And I think this one is kind of important, and some people have touched on it in some of the comments last lecture. Operators with higher precedence should appear in production rules that appear higher in the parse tree. So if you visualize the parse tree, if you have high precedence, like let's say multiplication over addition, do you think the multiplication should be higher in the tree or lower in the tree? Who says higher? People say higher. Kind of makes sense, right? Higher precedence should be higher in the tree. Who says lower? A few more people. So let's actually look at it. So our evaluation is a post-order traversal. So if we have a tree that looks like this, and if we do a post-order numbering, it ends up looking like this, right? So you start here, you go down left until you get to the end, so that's 1. Then you go down right, 2, and then once all your children are visited, you get to number this node, 3, go up here, 4, and 5. So when you evaluate, the operators that are lower, they get evaluated first. So what you want is your high precedence operators to appear lower in the tree and low precedence to appear higher in the tree. And that's how we resolve ambiguity. It's a bit, it's a bit opposite of what you might think, just sort of using the English description of higher precedence, higher in the tree. But just think about when you have a tree and you evaluate it, things that are at the bottom of the tree get evaluated first. Things that are at the top of the tree get evaluated later. Okay, does that make sense to folks? Okay. This is just an example of evaluating the parse tree. Remember, if you have something like 1 plus 5 times 6, you want the times to be lower in the tree than the plus, because that gets evaluated first. So you can review some of these slides if you still want to get some practice. Okay. We did talk about the tree, or we talked about the table. We said to make that table, the lower precedence goes at the top, higher precedence go in the bottom. And again, that just reinforces that idea that you want operators that have higher precedence to go lower in the tree. Okay, so getting back to Ant's question or comment. And this is the one that the Canvas seemed to freak out about answering. So, why is it bad to have an ambiguous grammar? What do people think? Yep.
We talked about this earlier, but with if-else statements, then it completely changes the way the Boolean expression or what should be evaluating to, I guess.
Yeah, with if-else, you need to be able to match the else with the right if, right? And if you don't, your program is just it's not going to make any sense, right? If you can't do that, then your program can do two different things. We don't really like that. Yep.
It could also cause undefined behavior, where depending on exactly how it's implemented, it could result in, let's say, if one architecture handles things slightly different than another,
Mhm.
it could result in things being evaluated in a different order and getting different outputs to the same inputs.
Yeah, and again, and it kind of goes to that idea that, if we have a program and if it's supposed to do one thing, and if it's allowed to do multiple things, that's never a good situation to be in. You want your program to do the same thing every time you run it, and that's not always the case in parallel programming, but when you're not doing parallel programming, that's what you want. What about what sorry, yeah.
Oh, I was just going to say, I guess it's kind of the same thing that people have been saying, but like having, more open-endedness, I'm assuming like for the future parts of like design compiler will just make it more edit. Like you have to deal with more development.
Yeah, anytime you can tighten up a spec, anytime you can make things more concrete and, not give like a lot of flexibility in inputs and outputs, or more closely, more thoroughly define what you expect the inputs to be, the better, right? What about what Ant was saying, where if you have integer arithmetic, that's associative. So should we care? Like, should we allow ambiguous grammars in that case? What do people think? Yep.
No, because I think maybe just in C, but since we can add integers and floating point numbers, there's a really good way, because you do need the order to be preserved for that.
Yeah, I think you might be okay if you just limit yourself to integers and make sure that's like the sub part of the expression you're looking at. But I think what you're saying is sort of down the right path to the answer that I like, which is you should avoid ambiguity, because otherwise you have to think about all these complex parts of expressions, floating point numbers, and you have to think about when it's allowed, when it's disallowed, and you're just going to melt your brain for a problem that is easily solved by just saying don't allow ambiguity, right? No need to add extra complexity. It's very easy to get rid of ambiguity in a grammar, as we're seeing, so might as well just not have ambiguity in a grammar. Yep.
Part of the answer is more of a question. In our homework, I think apply yet has ambiguity here in its grammar. I was wondering why.
Yeah, so in your homework, when you're playing around with ply, you can write an ambiguous grammar. And what it's going to do is it's going to make a choice for you, because it's going to realize that you probably don't want to do two different things. So it's going to make a choice for you, and it's going to give you a warning. Maybe you saw it, but you'll get a warning that says shift reduce warning. And yeah, I mean, in a perfect world that would be an error, because you should be the one saying how to resolve the ambiguity. But yeah, in modern frameworks, they will let you shoot yourself in the foot, just like how C will let you shoot yourself in the foot. So yeah, it's possible to specify ambiguous grammars. In practice, the tool will resolve it in a certain way, and sometimes that way will be the way that you want. But it's best not to rely on that. Yep.
Is there like a practical example where having ambiguity might actually
Ooh. I can't think of any off the top of my head. I think it's generally a known bad thing, which is why I think it should be an error in ply. But
I think of one of them. If you're doing the prefix increments in C within a other expression, I don't know why you would be doing it, but let's say you have like x plus plus x. That, depending on which order that gets evaluated, let's say x is set 1 at the beginning, if it evaluates the right-hand side first, then you would get 4. But if it evaluates the left-hand side first, you get 3.
Interesting. So I mean, so those rules do need to be resolved probably with precedence, right?
Yeah.
Yeah. And yeah, you don't want a program that simple to be doing multiple different things.
Yeah.
So, yeah. Yeah, and feel free to think about your own crazy examples and share them with the class, because this is stuff that I know we don't think a lot about, but it ends up being some of the foundations of the programming languages that we do use. Okay. Anyone else have any questions or comments on the quiz? Cameron?
When like C++ or something more complex, the compiler from those,
Yeah, I'm pretty sure that they are non-ambiguous, so I'm pretty sure given an input, they will always create the same parse tree for it. Whether they're proven to be unambiguous, I don't think so, because the real grammar for C++ is just insane. So I don't know that anybody's ever proven it, but I think in general it is not. Yeah, James?
I thought you could prove the grammar was ambiguous or not. Or sorry, there's no definite proof. Is that the case?
People who took 103 might know better, because there's all these theoretical properties. But I do think it's possible, if you express your grammar in like a production rule form, I think it's possible to prove if it is or isn't ambiguous. And in fact, Ply does that because it will warn you if it is ambiguous, because as it's building its algorithm, if it finds a place where it has a choice, like we saw up here, like if it finds that it has a choice and there's no way it knows which choice to make, it will complain, it'll give you a warning. So I do think if you express your grammar as production rules, you can determine whether it's ambiguous or not. The thing is that C++ can't be expressed as production rules. The grammar itself is more complicated for very strange corner cases. So yeah, that's why for C++ you kind of don't get that nice property. Yep.
Yeah, I'd say probably times. I know there are certain languages, I know like that the DoD uses, that you can mathematically prove the outcome for any inputs. That they use specifically for things like missile defense and things like that, where you need to be able to. It's or like even at NASA with the rockets and stuff like that, where it's if this is wrong and there is a bug in here, people die. So we have to make sure it doesn't happen.
Yep, there's a whole field of computer science where they do certification and audits, and they will, if a grammar's in one of those, they will make you kind of prove that it's unambiguous, and they'll make you prove a lot of other things about it too. So, yep.
Is it an expectation for compilers to, like, if given the syntax, they produce the same, like, understanding of semantics of the code? Like, is that like one of the trust?
If your program is well defined. So if you don't have divide by zeros, if you don't have data races, if you don't have out of bounds memory accesses, then your program should adhere to the specification. And however many different compilers that you have that implement the specification, you should get the same result. They go off-roading quite a bit, though. That's why Clang cannot compile the Linux kernel, because the Linux kernel is full of undefined behavior that GCC knows how to handle. So, yeah.
Yeah, I think it'll always, the program, when it runs, it'll give the same outputs and stuff like that, but how it gets there might not necessarily be the same.
Right.
It might use like sort of optimizations at the instruction level or something.
Mm-hmm. And even across optimization levels, like 0 to 03, it could compute them different. But as long as you have a well-specified program, then yes, should do the same thing. Good questions, good discussion. All right. Okay, let's review. And we've been talking about it quite a bit, but let's go back and talk more about our ambiguous grammars. I think I can go full screen because I don't think I have any demos. Okay, so we saw, how we got rid of ambiguity with precedence. If you had 1 plus 5 times 6, what you have to do is you have to take your grammar like this, and you had to split it up. So last time we talked about another source of ambiguity called associativity. And we saw that, if you have 2 plus 3 plus 4, and if we have our simple grammar like this that takes care of plus and multiplication, we saw that this was still ambiguous because we could get 2 parse trees for the same input. And while it didn't seem to matter that much for addition, it does matter for things like subtraction, because if you evaluate them, then you get different answers. Now the question is which one of these parse trees is right for this input? If we're thinking about meaning. Who thinks it's this one? A few people. Who thinks it's this one? Anybody? A few people? Okay, so what do we actually do here first when we're evaluating this? Do we do 2 minus 3 or do we do 3 minus 4? 2 minus 3, yep. And so you see 2 minus 3 is lower in the tree in this one. So this tree is actually the one that we want. So can we adjust the grammar to disallow this tree over here? What do people think? Well, we actually can. And we're going to see that in a second. We talked about left to right associativity. So that's, in subtraction, we move from left to right. We do 2 minus 3 minus 4. We also have right associative. We saw a couple examples of right associativity. We saw assignment, power operator. So those ones. So it does exist to have right associativity. And what you can do to get rid of ambiguity related to associativity is certain frameworks like Ply that you're using. It has some keywords that you can actually plug into and say, like, subtraction is left associative, power is right associative. You can do that. You're not allowed to for this homework, but you can. But we can also encode it into the production rules. So if you look here, I've just simplified the grammar just to be subtraction so that we can zoom in on subtraction. So we just have an expression, and an expression can be an expression minus an expression or a number. This is the parse tree that we do not want to allow, because this one lets us do 3 minus 4 and then 2 minus whatever that result is. We want to disallow this parse tree. So the way we do that, actually, I don't think is that difficult. We just don't let it expand on the right-hand side. What we say is an expression is an expression minus a number or a number. So if you're left associative, you only allow recursion on the left side. And now this parse tree is not allowed because this expression needs to be a num. So that number has to go there. That becomes 4. And then this expression gets expanded into expression minus a number, which is 3. And then that number is 2. So if you get rid of the recursion on the right side, you force the tree to go down the left side, which gives you a left to right associativity. Now again, if we had plus, like I was saying, we talked about it a little bit before, it might not matter a whole lot to have ambiguity with plus, especially if it's integers, but it's so easy to just disallow it. You just say, expression plus a num. And it's good design principle to disallow ambiguous grammars. So what you do then is, if you want to avoid ambiguity, if you're left associative, you make sure that you recurse on the left-hand side. If you're right associative, you just swap this. You do your recursion on the right-hand side. So given all of that, I think we can write a pretty expressive grammar at this point. So if we wanted to write an arithmetic grammar that had plus, multiplication, minus, division, power, and parentheses, we have our tokens here. Let's try to do it, and let's try to make it unambiguous. So in our table, what we do first is we talk about operator precedence. So what has the highest precedence out of all of these? Yeah? Parentheses, yeah. So we'll put parentheses down here. What has the next most highest? Yep. Exponent. Next most? Is it just multiplication? And division. Is it okay to have two operators at the same level? How do they get how do you disambiguate them? Exactly, left to right. So in associativity, we will disambiguate them. And what's up here? Plus, minus. Okay, so then I'm going to call this, let's call this expr, let's call this term, factor, unit. Those are the ones that are used in the book. But once we create our table, you're allowed to name these anything you want. Like I said, you can, normally, like I'm lazy and I would do like rule or name 0, name 1, name 2, name 3. You can do that. But yeah, always nice to give them a little bit more descriptive name. Okay, so an expression can be what? Yep. Plus expression plus or minus. Well, let's do it into 2 rows, because we don't really have some frameworks allow you to do regular expressions in your production rules, but we'll just do a different choice for that. So it can be an expr minus num or a num. Is that what you were saying? Okay, very, very close. But how should we adapt this? Max? We want to do term here. Oh, but would that allow us to do like 5 plus 4 plus 3? Yeah. Exactly. So what we want is we want term to go where we basically want to work our way down the tree because we want to be able to have multiple pluses and minuses in a row, right? So we want to be able to have expr up here, but as soon as we move down the table, that becomes the term. So again, hopefully you can start to see the recipe here. We get our rows, and then, because this is left associative, we recurse on the left-hand side, and then when we move our way down our table, we go to the next level. So this becomes a term, term, or term. And what is a term? Factor? Is that okay? I will. It can be a factor. What else can a term be? Well, we have our operators here. So it can be a term times, and then what goes here? Factor. We are moving our way down the table, or a term divide factor. So you can see there's this recipe. Left-hand side, operator, go down in the table. And now for a factor. So a factor, base case can be a unit, but what else can it be? Factor exp unit. Okay. Remember though, what did we say about exponent? What associativity does exponentiation have? Right to left. So we actually have to change this so we recurse on the right-hand side. So that becomes unit factor. And that way you evaluate your rightmost factors first, and then you move to your left. So you get your right associativity. Okay, and a unit, what can a unit be? Well, our base case, we're finally down here at our base case, so it can be a number. We can finally get our number. What else can it be? Max? Yes. You can put an expression in parentheses because that allows you to restart your precedence all over as long as you have those parentheses around it. And if we had like an ID, like a variable, that could go right here as well. Cool. Yep.
So the idea here is if you need to put like a term between parentheses and you just go up your list. Or like you start from unit and just go up your list and place an expression term.
Sorry, I don't know if I understand the question.
Is the reason we use expression in parentheses is because if we need to use like multiplication or whatever, then we can work our way up from the plus to multiplication.
Right. The reason why we have the expression here is if you have something like, I don't know, like 5 plus 6 times 3. If you wanted to say I want to do the addition first, you would put 5 plus 6 in parentheses, right? And what that would do is that would match this times with, like the first thing it would do is you'd get kind of a term times a factor. That factor would end up being 3. But then your term would come down here into unit and restart and become the addition. And because you're down low in your tree, that addition is going to be done first. So basically, like think about this. When you write a math formula, when you put parentheses, you basically restart the precedence within those parentheses, right? And this just lets you restart your precedence as long as you have the parentheses around it. Yep. All right. So I think this is a pretty decent milestone. We can now use production rules to express non-ambiguous grammars. We can encode precedence and we can encode associativity, right or left. So, not too bad. Does anybody have any questions or comments on this? Yep.
So the reason why it works is that just to make sure, like the one on the bottom is like the one on the top is going to get checked before the one on the bottom, right? Like x per plus term is evaluated before x per minus term, which is evaluated before term.
Yeah. And you're going to get your left-right associativity here. Yeah. So those basically you have to match those first, and those appear higher in your tree, so they get evaluated last, which is why our low our low precedence operators are all the way up here.
So you kind of just flow down through the 4 layers until you either hit none at the very bottom or you hit
Parentheses and
higher,
start going up.
order of operation.
Yep. James?
Are we just choosing to do left-right associativity because we just want to get rid of ambiguity? Because plus you can go either way. Minus, or no, minus actually, isn't it?
Right. So in minus, you have to. In division, you have to. For exponentiation, you have to, because they're non-associative operators. What we were saying before is because it's just so easy to get rid of ambiguity for like plus and multiplication, you might as well just not have an ambiguous grammar. Yeah, ambiguous grammars are bad. So in terms of, the meaning, we didn't really need to get rid of the ambiguity there, but it just makes sense. Yeah. You might as well. It's just super easy. Yep.
The reason why we have to define it like this is because, well, I mean, I know it creates ambiguity, but is it also because you mentioned that there's 2 ways to evaluate, like, there's 2 ways, there's like 2 ways. You can either recurse on the left or you can recurse on the right. Is that the reason why? Because I was just thinking, like, why can't you just program it to make it so that you can just recurse the tree on the or evaluate the left side first, or make the recursion tree on the left side first, then make the recursion tree on the right side. Yeah,
and in fact, Ply lets you specify that. Like it has like a certain like construct you can do to specify the associativity, and that's essentially what you're doing. Is you're telling Ply when it has a choice for like minus, you just recurse on the left-hand side. When you have a choice for exponentiation, you recurse on the right-hand side. So when you're building the algorithm, you could do that, and it just depends on where you decide to. Put your level of abstraction. Do you want to have a non-ambiguous grammar, or do you want to resolve ambiguity when you start parsing? And so, because your parsing tools might not always have the ability to disambiguate, I think it's good to learn how to encode it into your grammar. Yep?
Can I ask for you to do a very simple example of just flowing through the rules by hand?
With
this expression there?
Let's see, do we have one? I might have an example. Let's. I think I do have some examples, and we can do one. Let's do it next time when I can prepare it. But yeah, it's always a good exercise to flow through it.
Just because I think I get it, but I'm not 100% sure.
Yeah. Okay. Yeah. Let's do one next time. Okay. Yep.
I'm not sure if this is a very similar question to them, and I was wondering for the production for like addition plus. Why can't you write expression plus expression? Is it possible to make like an infinite tree? Or like, I'm wondering why do we have the term there?
Well, we have the term there because otherwise it's ambiguous. So even though the ambiguity might not impact your actual evaluation, you just don't want an ambiguous grammar. Like it's just not ever really considered a good thing. So this gets rid of ambiguity. You wouldn't necessarily get an infinite tree. Like once we start talking about algorithms, we'll see where like basically you can get into situations where the algorithm might not terminate, but we're already kind of there with expression, right? Like an algorithm can just like indefinitely just expand expressions. So I like that you're thinking ahead, but we'll see where that kind of comes up. Yep.
If you have like 5 plus 6 plus 7, would this grammar expand that properly?
Yeah, because you'd expand it in a way that's left associative. So 5 plus 6 plus 7, you just keep expanding the pluses on the left-hand side, and you kind of go down. Like it would look like a very lopsided tree.
So the first expression would be 5, term would be 6, and then term would end up be a number. And then how would you get that last number?
Because you just expand expression again to be expression plus term.
To the top if you're not further.
And then to get your last one, an expression can also be a term, and so that's going to be a long stick at the end. Yep.
So if you're implementing your own parse instead of using a parse generator, you would use something like Pratt parser, right, to do the ordering, precedence ordering?
There's many ways how to implement parsers, and I'm not quite sure if that's... you said Pratt parser?
Pratt, P-R-A-T-T.
Yeah, I've heard of those, but I don't actually know how you encode precedence inside of those.
It's basically each token that's there has a precedence, from like 1 to however many there are. It uses that as well as some other functions, the polygons parsing to determine which one to do first.
Interesting.
Yeah.
I'll have to look into that. We're going to eventually do a recursive descent parser. And I think it's a little bit harder to encode precedence into those.
Mm-hmm.
But there's many different parsers, and you should share on Piazza too, so that we can. Because Pratt parsers I know are known for being pretty straightforward.
Yeah, it was pretty straightforward. That's, yeah.
Cool. Yeah. So yeah, let's share a link so we can check it out. All right. Any more questions? Okay. Let's continue on. Just as a reminder, C++ does have these tables, very similar tables to the ones that we've been making. And they have, all of their operators, if the internet's going to work. They have 15 levels of precedence, and each level says whether it's left to right, right to left, and all the goodies like that. So, I do think it is worth some time looking at how this is implemented in real languages. Okay, let's get started with the next topic, which is now that we can specify an unambiguous grammar, how do we actually implement the parsing? So, one of our goals is given a string S and a context-free grammar G, determine if G can derive S. Basically, we said that means S is part of the language of G. What we're going to do is we don't actually end up building the parse tree exactly, but we're going to implicitly try to derive a parse tree. And you're going to see how that looks in a second. There are two different approaches for doing this, and each one has trade-offs. As always, it's computer science, so it's basically the study of trade-offs. What you can do is you can do top-down parsing. What top-down parsing does is, let's say we had our input 2 plus 3 plus 4. We had our expression. Top-down parsing essentially, as you might expect, starts at the top and tries to do something like this. Tries to go from the top and derive a parse tree going from the top. Some of the pros of top-down parsing is the algorithms tend to be simpler. Overall, I think it's generally considered to be faster than bottom-up. And you get some nice properties in that you can do error recovery and stuff like that. And so we'll see some of that. Some of the drawbacks is that it's not as efficient on arbitrary grammars, meaning you can give it really bad grammars. Typically, these grammars don't show up in programming languages, but there are some pathological grammars that top-down really struggles with. And on top of that, sometimes your grammars need to be rewritten. And in fact, we're going to have to rewrite our grammar to feed it into a top-down parser. The other way that people do parsing is bottom-up, which in bottom-up, you essentially start off with your lexemes, and then you try to build your tree from the root up to the top. And so bottom-up, they can really handle many grammars naturally. So Ply in your homework, that is behind the scenes going to be doing a bottom-up parser because those just tend to work really well in parser generators. The nice thing is, and there were some comments about it, is, bottom-up parsing can basically make those decisions about precedence and associativity. During the algorithm, it can kind of say, hey, I have a choice here to do a multiplication or an addition. Which one do I do first? That, in a bottom-up parser, that's a choice that you can really make explicitly, and you can encode it in, which is one reason why Ply has that option that you could use. I do think that the algorithm is complicated. It's kind of much more complicated. And in most cases, it ends up being slower than top-down. So what we're going to do in this class is we're going to focus on top-down approaches. And so the algorithm, the way we're going to design this is, and maybe some of you write your programs this way, I know that I do, is sometimes I start at the top of my algorithm and I write a bunch of functions, and I don't implement all of the functions, but I kind of say, these are the functions that I need, and then you drill down and implement the functions that you need. I think that's a good way how to write code. And we're going to look at an algorithm, and we're going to leave some functions unimplemented for now. And you might think, we're going to, these might be really hard to implement in the future, but, we'll get there. So let's see, this slide is kind of busy, but let's kind of walk through it. So over here, here's the grammar that we're going to do. This is grammar, does additions or multiplications. This is an ambiguous grammar because we can basically choose which one to expand when we do operations. But, for the sake of the parsing algorithm, that's okay. We'll move on to the non-ambiguous ones, especially in your homework. But, this allows an expression op unit. Unit can be an ID or parentheses. So very similar to the type of grammars that we've been seeing, just plus, multiplication, and parentheses, and expressions. Now what we're going to do is the algorithm. We're going to have a start symbol. So to begin with, we're going to have the root is going to be the start symbol. We're going to have this variable called focus. Focus is the current non-terminal that we're looking at. So we're going to set that to be the start symbol. We're going to have a stack. Initially, our stack is going to be empty. Now, here comes our lexer. Remember we talked about the API for the lexer. It is going to grab the next token to match. We're going to get a token, and that's what we want to match. So the parser, it shouldn't be too surprising that the parser algorithm has a scanner behind the scenes to get our lexemes. Then what we're going to do is we're going to iterate while true. So we're going to iterate essentially until we have an empty stack. But what we want to do is, if what we're focusing on is a non-terminal, so if it's a production rule, then we pick the rule, we pick the production option to expand on. So, if we're an expression, we can pick rule 1 or we can pick rule 2. If we're a unit, we can pick rule 3 or rule 4. So this is what I was saying. We're going to leave this pick next rule. We're going to kind of assume that we have a magic function that tells us which rule to pick. And then once we pick a rule, we have our sequence of non-terminals and terminals. I'm calling them B1, B2, B3, up to Bn. For example, that's going to be expr, op, unit. If you pick number 1, if you pick number 3, that's going to be open parenthesis, expr, close parenthesis. And we're going to put those onto the stack. So the stack is going to have those symbols on it. And then we're going to change our focus to what was on the top of the stack. So for example, if we picked rule 1, our focus would be an expression. We would put op and unit onto the stack, and we would focus on our next symbol, which would be an expression there. If what we're focusing on is a terminal, so if it's an ID or an open parenthesis or a close parenthesis, then what we do is we just check to see if that terminal that we have is equal to that lexeme that we got from our scanner. If it's equal to that lexeme that we got from the scanner, we get our next token using that token API that we used before to get a new lexeme that we want to match, and we just pop the next thing off the stack that we're searching for. And finally, if we're done with the string, if 2 match, remember that comes from our lexer. If that is none, so there's nothing left in the string to lex. And if we don't have anything to focus on, then, which means our stack was empty, then we can accept that string. So I know this is a lot to kind of drink in now, but let's kind of walk through it with this string a plus b times c. So if we kind of walk through that, when we initialize this, to match, we're going to get our first token. Our first token is going to be an open parenthesis. So we're going to assume that we have a token for that. Our focus is also going to be open parenthesis because, actually, let's see. Is it going to be that? Our focus is going to be, it's going to be the production rule. So focus is going to be an expr. Okay, the I string, input string, is what we have left to match. So that's sort of peeking into the scanner. So if we peek into the scanner, this is what's left. And our stack right now is empty because we haven't pushed anything onto the stack. So that's kind of our starting state. Okay, so now let's go into the algorithm. So our focus is a non-terminal. So that means we need to pick our next rule. Expression. So we basically get to pick 1 or 2. So like I said, for now we're assuming that this is sort of magic. We know which one we need to pick. So expanded rule, we're going to pick 1. This is going to be an expr op unit. And I'm keeping this table over here. This isn't what the algorithm is building. This is for us to sort of keep track of how the algorithm is going. So we pick 1. That gives us some elements on our stack. We have op unit. The first element there was expression, but that expression is just going to be our toFocus. So our toFocus stays the same as expression. OK. So now let's go around again. Our focus is a non-terminal. It's expression. We have to pick the next rule. So our next rule is 1 or 2. We're an expression. Because, again, we're assuming that we know the magic rules here. We need to match our parentheses. So we're going to pick rule 2. That's going to expand this to open parenthesis. Remember, we're trying to match this string. Open parenthesis, expr, close parenthesis, op, unit. Right? And so then, if we pick that one, our stack becomes, let's see, what does it become? Expr, close parenthesis, and then we have our op unit. That was there from last time. So we keep pushing things onto the stack. And then our focus becomes that first element, the open parenthesis. Is that making sense to everybody? OK, we go around again. Our focus this time is, it's not a non-terminal, so we come down here. So our focus, is that equal to toMatch? It is equal to toMatch. So let's get our next token from our I string, which is going to be an ID A. And we can chop A off from that. And our focus gets popped from the stack, which becomes this expression. So essentially, we're keeping a stack. You can think of that as keeping a stack of what we're trying to match. We always pick, we're basically doing a left derivation. So, whatever is on the leftmost side, we're walking through, and we're continuing to do it. OK, so, if we come here, and we have the expr again, let's see, we have to map this closing one. What we're going to do is we're going to pick rule number 1, which is going to give us, let's see, that's going to give us an expr, and we are going to get an op unit there. This is going to be an expr, and so on and so forth. So kind of keeping to do this, we picked this one again. In parenthesis, expr op unit, op unit. So hopefully people can kind of see where this is going, where we sort of pick the rules, and you can see what we need to match. So this table, again, is just sort of guiding us down this algorithm. So again, let's see, where are we at? Expr here, we want this to become a unit. Because there's nothing else to push on the stack, that's fine. This unit comes down. And then what we probably want the unit is to become an ID. So we pick rule number 4. That gives us an ID here. Once we get that ID, we can match. We can match that, get our next token, which is a plus. Chop that one off. And then we get to pop from our stack, which means we're an op up here. And again, it's a little bit tedious going through this by hand, but I think that you should sort of read this. The book goes through it as well. And you can kind of see how you basically keep track of a stack. If you have a terminal, then you basically use your lexer, you grab your token, you see if that's what the terminal is that you're trying to match. If you have a non-terminal, you get to pick a rule, and you get to expand it, and then you add those components, both terminals and non-terminals, to your stack, and you essentially are popping and matching as you go along. Now there's, like I said, there's a lot of magic kind of here, especially in this pick next rule. This, we kind of just assumed that we knew which rule to pick. Is this something that we're going to be able to do? What do people think? Well, we will eventually, but it takes a little bit of work. Okay, so we're not going to go through the rest of that just because it's kind of systematic and algorithmic. But I do suggest trying it out on your own and walking through this algorithm. But essentially what we need to do now is we need to focus on trying to take the magic away from this rule. If we can know which rule to pick next, and if we can do that, with basically if we can pick the right rule 100% of the time, then all of a sudden this algorithm turns into a very nice and very efficient algorithm, and that's where we're essentially going to go. So let's see. The slides do have the rest of the derivation there, so feel free to have a look at those. It is about 3:44, so let's call it good for today and keep talking about algorithms next time. All right, thanks everyone.